Alright, so in the last couple of classes, we've dealt with flow over flat plates, both in the laminar and turbulent case last week, or last class. Today, going to go through other geometries, mainly circular geometries, cylinders and spheres, specifically in cross flow. So I have my cylinder and flows coming across the cylinder. So in other words, this is my cylinder, my little pen, flows coming across this way, it's not going that way. So for this reason, or for this situation, we have empirical relationships, so derived experimentally, and generally what they have is something that looks like this. So my Nusselt number, now h times d over k, so d being the diameter. In the flat plate case, we have the length. For this case, we want the diameter, so diameter, again, which way the fluid is going go over that distance of the diameter. So that's how my Nusselt number is now defined. And the relationship looks like some constant c times Reynolds number to some power m, Prandtl number to the 1/3 power. C and m, again, just constants. We're going to find those in a table. See that in a few minutes. And then for the Reynolds number, I need all, and Prandtl number too, I need all the fluid properties evaluated at the film temperature, just like we did last class. So in our equation for the Nusselt number, C, R to the m, Prandtl number to the 1/3 power. Again, we have values of constants that were found experimentally. So for different values of the Reynolds number, I have different values for the constants, C and m. So small Reynolds numbers, 0.4 to 4, C, 0.989, m, the exponent, 0.33. Then as we go up, higher Reynolds numbers, values of C go down, so 0.911, between 4 and 40. Values for the exponent, m, go up, so in this case 0.385, then just whatever value we have, use the right values for the constants. So if I have a Reynolds number, say 10,000, 10,000 is between 4,000 and 40,000, so I'll use 0.193 as my constant, 0.618 as my exponent of the Reynolds number, and then that gives me my Nusselt number. Then just like before, now once I have the Nusselt number, I can find H, I can find Q. So that previous expression we just saw is the simplest expression for flow over a cylinder. I may have not been clear earlier, but that expression and those values for C and M are purely for the cylinder case. We'll get to the sphere later. So for a cylinder, have those values. We'll also have other expressions, so the textbook has a few other ones. The most notable is this guy here. It's a lot more complicated. 0.3 plus 0.62 Reynolds number to the 1/2 power, Prandtl number to the 1/3 power, divided by 1 plus 0.4 divided by Prandtl number to the 2/3 power, whole denominator to the 1/4 power, all multiplied by 1 plus Reynolds number over 282,000 to the 5/8 power, whole thing to the 4/5 power. So a bit more complicated, but the nice thing about this guy is that he's valid for more circumstances, more fluids, more ranges of Reynolds numbers. The table we saw before started at a Reynolds number of 0.4, only went up to a Reynolds number of 400,000. This is valid for larger ranges, so if you're outside those ranges that we saw on the previous table, this guy's a good guy to use. You can also use this guy if you want in general, so even if you're in those ranges, this guy still works as well. Those should give you values that are fairly close to the values that the table will give you. In addition to those circular cylinders, there's also the case of having non-circular cylinders, so having sort of elliptical or even kind of square ducting type of things. In this case, we have table 7-3, page 329. Go back to the simple equation, Nusselt number, C times Reynolds number to the power m times Prandtl number to the 1/3 power. And there's a table that similar to the one we saw before, but different values that have values for C and M for different values of Reynolds numbers. Generally, that table is good as long as I'm dealing with gases, so Prandtl numbers in the neighborhood of 0.7. Most gases are kind of in that range. Liquids not necessarily. And also, just like the other table, there's going to be a range of Reynolds numbers where this is good for. So again, whatever the Reynolds number is, find it based on that table, then find the value for C, value for M, stick it in there, and there's your Nusselt number. So for the sphere, just like the cylinder, you have many choices in terms of what equation to use. A lot of them are based on the conditions, so what's exactly happening, what the Reynolds number is, things of that nature. So page 300 in the textbook has a summary of all of those. The most comprehensive, most useful one that will pretty much suffice for this class is this guy here. So Nusselt number, little d down here just means that it's based on diameter. So just like we did for the cylinder, when you go to calculate h, make sure it's based on the diameter. Same thing for the Reynolds number. There's a length in there. The length in there is the diameter. So that's all that little d means, is that use the diameter for any length that you may encounter. So Nusselt number 2 plus 0.4 Reynolds number to the 1/2 power, 0.06 Reynolds number to the 2/3 power, Prandtl number to the 0.4 power. And then you have this factor of viscosities. So viscosity at the free stream temperature, U infinity, and viscosity at the wall temperature, UW, that ratio to the 1/4 power. Note, for this equation, which is different than all the other ones that we're going to see, fluid properties evaluated at the free stream temperature, so at T infinity, not the film temperature. Obviously, my wall viscosity, that's the viscosity of the fluid at the wall temperature, U infinity, viscosity of the fluid at the free stream temperature. So everything in here, in terms of Reynolds number, the densities, viscosities, all at the free stream temperature, and that gives you the Nusselt number in that case. Again, valid for certain Reynolds numbers, certain Prandtl numbers. If you're outside those ranges, again, textbook, page 300, has other equations to use in those circumstances. So we've seen quite a few geometries and quite a few different equations you can use for these different geometries. Good summary tables given in the textbook, table 7-7, page 354 to 355. So if you're looking for, okay, I have this certain geometry, this certain Reynolds number, what equation should I use? That's a good place to look. So just look through it. This is my geometry. Here's the Reynolds number I have. Here's maybe some other parameters that are having my problem. I can use this equation. Sometimes there's maybe 2 or 3 equations you can use. As long as you have all your bases covered, the right geometry, the right range of Reynolds numbers, any of them will be fine. So to do an example of this, a 5 centimeter diameter cylinder, surface temperature 80 degrees Celsius on the surface, placed in a flow of nitrogen, so coming in at 5 meters per second, temperature of 10 degrees Celsius, and pressure of 2 atmospheres, flows across my cylinder. Want to know the heat loss per unit length of my cylinder, so in and out of the board, per unit length, what sort of heat is being lost by my cylinder. So solution to this guy, follow the same procedure we did last class for my flat plate. First thing you want to do is find the film temperature, then find all the fluid properties at that temperature, then I can find the Reynolds number. Once I have that, I have basically all my conditions to see which is the right equation to use for the Nusselt number. So then find the Nusselt number, then find H, then find my heat transfer Q. So that's where we're going to start. So film temperature, wall temperature, and free stream temperature divided by 2, the average of the two. So 80 and 10, average of those is 45 degrees Celsius. So that's my film temperature. And now I want to evaluate all my properties of nitrogen at that temperature. So table A-4, I have a viscosity of 1.86 times 10 to the negative 5 kilograms per meter second. Thermal conductivity, 0.0271 watts per meter degree Celsius. Prandtl number, 0.714. And then in terms of the density, last class I found the density in the table and multiplied it by 2 for 2 atmospheres. I could have done that as well this time. Instead, I'll do it a different way using the ideal gas law. Density is pressure over R and T. R for nitrogen, I think that's in the table as well, if you can find it, 297 joules per kilogram Kelvin there. 2 atmospheres, 2 times atmospheric pressure. And then my film temperature, 45 degrees or 318 Kelvin. Putting all that in gives me a density of 2.15 kilograms per cubic meter. So now that we have the fluid properties, the next step is to find the Reynolds number. So Reynolds number, density times velocity. In this case, I'm dealing with length as a diameter. So diameter divided by viscosity, density of 2.15, velocity of 5 meters per second, diameter 5 centimeters or 0.05 meters. The viscosity we found on the last screen gives me a Reynolds number of 28,900. So this 28,900, I flow over a cylinder. So beginning of class, we saw that table that has certain values of Reynolds number. This guy is between 4,000 and 40,000. So on that table between 4,000 and 40,000, I can use this equation, C times Reynolds number to the n power, Prandtl number to the 1/3 power to find my Nusselt number. Values of C from the table, 0.193 m, 0.618 for this case. So plugging that in for Nusselt number, 0.193, my Reynolds number of 28,900 to this power, 0.618. Prandtl number we found before to the 1/3 power gives me a Nusselt number of 98.5. So now we can relate that Nusselt number to the heat transfer coefficient H in the usual way. Nusselt number H times, in this case again, my length is D, so H D over K is my definition of Nusselt number for these circular geometries, which means that H is K over D divided by my Nusselt number. So K, 0.0271, diameter 0.05, Nusselt number we just found, 98.5, gives me a heat transfer coefficient of 53.4, is my value of H, watts per meter squared degree Celsius. And then to find my Q, standard equation, H times A, T wall minus T infinity. Area in this case for my cylinder is pi dl, and then I'm asked for the heat transfer per unit length, so I can divide by that L and get Q over L, pi times D times H, T wall minus T infinity. So plug all those numbers in, pi, diameter of 0.05 meters, H we just found is 53.4 watts per meter squared degree Celsius. Wall temperature of my cylinder was 80, free stream temperature of the nitrogen was 10, gives me a total heat loss or heat transfer per unit length of 587 watts per meter.